Scientists unlock secret to faster charging supercapacitors through ions. The model predicting ion movement in complex nanopore networks could revolutionize energy storage technology. Researchers led by Ankur Gupta at the University of Colorado Boulder have discovered how tiny charged particles, known as ions, move within a complex network of minuscule pores. This breakthrough, highlighted by Gupta, an assistant professor of chemical and biological engineering, could pave the way for the development of more efficient energy storage devices, such as supercapacitors. Before we proceed, we kindly ask you to support us by liking this video, subscribing to our channel, and activating notifications to stay updated on our latest content. Remember, sharing is caring. Supercapacitors, like batteries, are energy storage devices. They charge faster than batteries, often in a few seconds to a minute, but generally store less energy. They're used in devices that require storing or supplying a burst of energy over a short span of time. In your car and in elevators, they can help recover energy during braking to slow down. They help meet fluctuating energy demand in laptops and cameras, and they stabilize the energy loads in electrical grids. Given the critical role of energy in the future of the planet, I felt inspired to apply my chemical engineering knowledge to advancing energy storage devices. It felt like the topic was somewhat underexplored and, as such, the perfect opportunity, explained Gupta. While various chemical engineering techniques are employed to analyze flow within porous materials like oil reservoirs and water filtration systems, their application in certain energy storage systems remains underexplored. Thus, the study introduces a model to predict electrolyte transport in complex networks of slender pores. The framework accelerates numerical computations by 6 orders of magnitude without compromising accuracy. This model is then used to investigate the influence of connections and pore size distribution on the charging timescale of electrical double layers and to predict structure-property relationships. The discovery is important not just for storing energy in vehicles and electronic devices, but also for power grids. In these grids, where energy demand changes, efficient storage is needed to prevent waste during low-demand times and ensure quick supply during high-demand times. Supercapacitors beat batteries for rapid charging, extended lifespan supercapacitors, which store energy through ion accumulation in their pores, offer rapid charging and longer lifespans compared to batteries. Gupta emphasized the speed advantage of supercapacitors, stating that improving ion movement efficiency could further accelerate charging and energy release. Batteries operate via reactions in which chemical species give or take electrons. Supercapacitors, in contrast, do not rely on reactions and are kind of like a charge sponge. When you dip a sponge in water, it soaks up the water because the sponge is porous. It contains empty pores where water can be absorbed. The best supercapacitors soak up the most charge per unit of volume, meaning they have a high capacity for energy storage without taking up too much space. The research challenges Kirchhoff's law, a long-standing principle governing current flow in electrical circuits. Unlike electrons, ions move through a combination of electric fields and diffusion. The researchers found that their movements at pore intersections deviate from Kirchhoff's law. These findings hold potential for improving supercapacitor design and enabling 3D printed microscale electrodes for wearable energy storage and supercapacitors in Internet of Things applications. The abstract of the study stated that their network model provides results up to 6 orders of magnitude faster, enabling the efficient simulation of a triangular lattice of 5,000 pores in 6 minutes. Scientists can increase a material's capacitance or ability to store charge by making its surface porous at the nanoscale. A nanoporous material can have a surface area as high as 20,000 square meters, 215,000 and 178 square feet, the equivalent of about 4 football fields, in just 10 grams, 1/3 of an ounce of weight. Over the past 20 years, researchers have studied how to control this porous structure and the flow of ions, which are tiny charged particles, through the material. Understanding the flow of ions can help researchers control the rate at which a supercapacitor charges and releases energy. But researchers still don't know exactly how ions flow into and out of porous materials. Each pore in a sheet of porous materials is a small hole filled with both positive and negative ions. The pore's opening connects to a reservoir of positive and negative ions. These ions come from an electrolyte, a conductive fluid. For instance, if you put salt in water, each salt molecule separates into a positively charged sodium ion and a negatively charged chloride ion. When the surface of the pore is charged, ions flow from the reservoir into the pore or vice versa. If the surface is positively charged, negative ions flow into the pore from the reservoir, and positively charged ions leave the pore as they're repelled away. This flow forms capacitors, which hold the charge in place and store energy. When the surface charge is discharged, the ions flow in the reverse direction, and the energy is released. Now, imagine a pore divides into 2 different branched pores. How do the ions flow from the main pore to these branches? Think of the ions as cars and pores as roads. Traffic flow on one single road is straightforward, but at an intersection, you need rules to prevent an accident or traffic jam, so we have traffic lights and roundabouts. However, scientists don't totally understand the rules that ions flowing through a junction follow. Figuring out these rules could help researchers understand how a supercapacitor will charge. Engineers generally use a set of physics laws called Kirchhoff's laws to determine the distribution of electrical current across a junction. However, Kirchhoff's circuit laws were derived for electron transport, not ion transport. Electrons only move when there's an electric field, but ions can move without an electric field through diffusion. In the same way, a pinch of salt slowly dissolves throughout a glass of water. Ions move from more concentrated areas to less concentrated areas. Kirchhoff's laws are like accounting principles for circuit junctions. The first law says that the current entering a junction must equal the current leaving it. The second law states that voltage, the pressure pushing electrons through the current, can't abruptly change across a junction. Otherwise, it would create an extra current and disrupt the balance. Since ions also move by diffusion, and not only by the use of an electric field, my team modified Kirchhoff's laws to fit ionic currents. We replaced voltage V with an electrochemical voltage, Phi, which combines voltage and diffusion. This modification allowed us to analyze networks of pores, which was previously impossible. We used the modified Kirchhoff's law to simulate and predict how ions flow through a large network of nanopores. We employ the framework to study the impact of poor connectivity and polydispersity on electrode charging dynamics for pore networks and discuss how these factors affect the timescale, energy density, and power density of capacitive charging. Gupta notes that previously, ion movement was described only in single pores. But this research allows for the simulation and prediction of ion movement in thousands of interconnected pores within minutes. That's the breakthrough. We've uncovered the missing piece, Gupta concluded. That concludes today's discussion. Please remember to like, comment, and share this content with fellow enthusiasts and relevant forums. Thank you, and we eagerly anticipate your presence in our next episode.